Okay. So my name is Belén Martín-Matute, and I want also to start by thanking the Göran Gustafsson-Stiftelse for this wonderful prize. And I will try to tell you a little bit what we are doing in the laboratory. So we are trying to develop catalytic methods to construct organic molecules efficiently. Why do we need to study catalysis? Because it is all around us. We need catalysts to make pharmaceuticals, to make food, to make polymers, soap, everything. But also we need catalysts to destroy harmful chemicals, like for example in the catalytic converter in our cars, also to purify water, for example. And catalysis has affected humanity tremendously, and this is a very dramatic example, I would say the most dramatic one, and it is the production of ammonia. And this chemical is made by combining nitrogen and hydrogen on a solid catalyst. And millions of tons of these chemicals is done every year. And actually, it is this process, the one responsible for the growth population in the world, from 1.6 billion people before this process was discovered to 6.7 million as we know it today. When we do development of catalysis, we really have to think, it is our responsibility nowadays to think about sustainability. And in the catalysis that we do in my laboratory, we do that by thinking about atom economy. That is to say that everything we put in the reactions must be of some use, must end up in the final product. Save energy, so develop processes that do not require much energy, reduce cost, produce less waste, and whenever possible also make use of renewable resources, such as carbon dioxide, for example, or lignin degradation products. It's also very important in my research to have a very good relation with the industry so that we can transfer our innovations to the society. So how does a catalyst work? A catalyst is diminishing the energy that we need to put into a system so that the substrate is converted into the product. In some cases, the chemistry does not even happen at all if we don't have a catalyst. And these are some of the catalysts that we use in my laboratory, and there are mainly two different families. We have the homogeneous catalysts, and those are catalysts that are dissolved in a liquid phase, like for example this, and everything, reagents and product are in the same phase. And then we have heterogeneous catalysts, and maybe it's a little bit difficult to see, but in the heterogeneous catalysis we have the catalyst in the solid phase. So when the chemistry is done, we can filter, recycle the catalyst, and then reuse it. And we use these catalysts, they are mostly based on transition metal complexes. We have also some organic catalysts, and we use them to make efficiently carbon heteroatom bonds, particularly carbon halogen, carbon nitrogen, carbon oxygen, also for transfer hydrogenation chemistry. And very important for us is to know how the catalysis happens so that we can develop a better process or even discover a new reaction in chemistry. So a summary of our halogenation chemistry is here. We can now make very efficiently carbon fluoro, carbon chloro, carbon bromo, carbon iodide bonds. And we use a very simple catalyst, which is commercially available, that works in water at room temperature. So it's very efficient and it's extremely selective. So we make the carbon halogen bond exactly where we want to make it. We also work a lot on making carbon-nitrogen bonds, since amines are very common motifs in bioactive molecules. And this is just one example of the reaction. And for this, we designed a catalyst that it was working really well, giving excellent yields under, with high selectivity, but it needed some high temperature. So in this case, for example, we studied the mechanism, and by doing that, then we can identify where is the weak point in the catalytic process. And in this case, it was that there was a resting state. So we just modified the catalyst in a way that we could not make this resting state. And now we can do the same chemistry at room temperature instead of heating at 110 degrees. And the very last slide I want to show is about our heterogeneous catalysis, and for this we use porous materials that are composed by metal clusters and organic linkers, and inside these pores we put the catalyst, either metal nanoparticles or transition metal complexes, and these are very fascinating materials, and this is kind of macroscopically how these materials would look like. So they have an enormous surface, and we put the catalyst inside so that the reactants go in, react, and the products go out. And these materials, many of them, they are even flexible, so they can really adapt to the shape of the catalyst. And this is very important for heterogeneous catalysis, where diffusion becomes a very important parameter. And just one example using this catalysis where we used such a heterogeneous catalyst with a palladium nanoparticle inside to make a carbon-carbon bond. And we can do this in water at room temperature in half an hour. Actually, we have processes now that take only 30 seconds. So it's really an efficient way of doing catalysis. And yeah, I just want to thank my fantastic research group, present and past members, and my collaborators, and those who has inspired me to be doing what I'm doing today, and of course funding, and you, of course, for this fantastic prize. Thank you.